record with my camera at home, I will put videos of that on YouTube. So you'll basically have two copies of the lecture, one on Zoom and one on YouTube. Okay. The one on YouTube I just started because I forgot. Okay. All right. I also want to talk about particles and fields and then field lines. So just as a reminder of what an electric field is or what it's useful for, the field concept is useful in determining forces and charges in complicated systems or in situations where Coulomb's law is not valid because Q times V is valid in any situation. The electric field sets up a condition in space and time that characterizes its behavior or its effects on charged particles. Basically, it's a function of space-time where you associate a vector at every location in space, or space and time. And in math, the field is an assignment of a scalar, a vector, or some other physical quantity, not a mathematical quantity I don't want to get into, at each point in space where the field is defined. So, the other day we finished off on how do we calculate the electric field due to a continuous charge distribution. So I picked a problem that I want to show you that's fairly complicated, although the integral is easy. And one of the things I said the other day is if we're going to do these kind of problems, we want to learn how to set up the integral for us to be able to do the calculation. I have some arbitrary system of charges. I want to find the field at point P, and what I said was I have to break this up into a bunch of teeny tiny charges, small enough so the field is constant over the element. And I want to calculate the field due to this elemental charge, dq. I write an expression for dq. And I write an expression for dE. And then what I do is I sum the electric fields due to all the dq's that make up the system. Well, if those are infinitesimally small, that sum becomes an integral. In order for us to be able to do the calculation, I need to write an expression for r squared, r hat, and dq. And so what I list there in the PowerPoint notes there is really a method that you should try to use to be able to do these problems. So the first thing you want to do is choose a coordinate system, then write an equation for dq. Determine r squared. Now r squared is the square of the magnitude of the vector that's directed from the source of the field to the point at which you're calculating the field. You want to determine r hat, but and again, r hat is the unit vector that goes from the source of the field to the point at which you're calculating the field. But if your system has symmetry, and a lot of the problems will have symmetry, then you can ignore the components of r hat that will not contribute to the integral. The example I will do has this built into it. So once you find dq, once you find r squared, once you find r hat, you put this all together into this expression, and then you integrate it. And typically the integration is the easy part of the problem. Setting it up is the hard part. And you'll notice in the homework for chapter 23, you will see problems that are geared to help you learn how to set up the integral. So one of the problems is problem number 9. Basically, as you go through a bunch of exercises to determine what dq is for various charge distributions. So students have a hard time with this, and I think the second hardest thing for students is determining what r hat is. So I want to determine the electric field hold on a second, I don't know why it's doing that. That PowerPoint's acting weird. I want to calculate the electric field due to a ring of charge where the charge is uniformly distributed around the ring, but I want to find a field at a point P above the plane of the ring and along the axis of the ring. Now, we talked about in class, what is the field at the center of the ring for a uniformly charged ring? And we got 0. We argued by symmetry that the field would be 0. Now I want to look at a point outside of the plane of the ring, but along the axis of the ring. And now I want to calculate the field at that point P. And this is a complicated problem. It turns out that when you set up the integral is actually very easy to do. Give me a second here to erase the board. And I'm going to try to redraw that on the board. I'm not an artist. Let me draw my coordinate system. Let me draw my ring of charge. And let me draw point P. And my coordinate system is that. And I want to determine an expression for dE first. So I want to know dE. So basically I need to know what's dQ, what's r hat, and what's r squared. In fact, I'll do the second, that one's easier to do. So I want to break this up. I want to break this ring up into small pieces. So I'm going to look at the ring from the top view. I'm going to break it up into pieces small enough so that the density is constant over that ring. But also I want to break it up into pieces small enough so that the field is constant over that ring. So, over that piece, sorry. My radius is A. And I want to break it up into this arc length. This is a small angle, very small d theta. We know that dq is lambda dx, which I can't really write x in this particular case, but I want to write s because really this element of length is an arc length. And so I'm going to write it as ds. And if the charge density is uniform and the total charge is q, then the charge density is the charge over the length of this ring. Well, the length of that ring is the circumference of that ring. And then this arc length ds is basically radius times the angle, which in this case is infinitesimal. These cancel and you get and I hope you realize, I hope you see that this expression for dq makes sense, because if I integrate my dq from 0 to 2 pi, this 2 pi cancels, and I get the total charge q. So I'm done with that part already. So I already know what my dq is. Okay? Now I want to figure out what r squared is. Let me do r squared. I want to know the distance from between p and my ds. So let me draw that in my picture. Here's my arc of ds. And dq is I want to know the distance from here to here. This is A. This distance is Z. This is a right triangle. So the blue hypotenuse is easy to determine. R is the square root of Z squared plus A squared. And remember, R is the length of the vector that goes from the source of the field to the point at which you're calculating the field. And so R squared then is Z squared plus A squared. So the last thing I need to do is to determine R hat. Yeah, I'm sorry, Alex. Yeah, that's a lambda next to the ds. I didn't see your question. We want to determine where r hat is. It's a unit vector that points from this point to this point. The element of charge to the point at which you're calculating. So let me draw an arrow. That's r hat. I'm going to denote this angle is alpha. My writing is getting smaller, I apologize. This is a vector in 3 dimensions. It has an x component, it has a y component, and it has a z component. The z component is this one right here. It's a unit vector. Its length is 1. The unit vector is going to be basically cosine of alpha. But then there's an x and y component. There's components in the plane of the ring. Now, I know that the electric field is going to be directed towards point P. This is a positive charge. Now imagine drawing that arrow all the way around the ring. Okay, that black arrow that I just drew, I draw it all the way around the ring. I draw one for every location all the way around the ring. And I add all those vectors together. And what you'll notice is all the z components of this vector, if I draw them all the way around the ring, they point upward. But what about the components in the plane? If I draw that vector all the way around the ring, I copy it all the way around the ring. What happens to the x and y components? You'll have a vector in this plane like this, and a vector in that plane like that, another one here, and another one here. If you go all the way around the ring, those vectors are going to cancel. So all the components that are in the plane of the ring are going to cancel when I do the integration. Then when you think about the x and y components, I mean, they're going to be in the plane here. And if I go all the way around, they're all going to cancel when I integrate all the way around. In other words, when I sum all the vectors, the ones in the plane of the ring will cancel. It's because I have symmetry in the problem, which is nice because then I don't have to write out all the components. I can just say this, okay? And I know that these components are going to cancel. In fact, if you're interested in knowing what it looks like, it's going to look like this. Okay, but if you integrate around theta, if you integrate this from 0, either one of these two from 0 to pi, you're going to get 0. So we know from symmetry, this one's going to cancel. So I'm not even going to worry about it. So I'm just going to write the following up here. And I'll just do that, but I know these are going to cancel. I'm writing the dots there. It says that I know there's other components, but they're not going to play a role when I complete the integral. R hat does have to be a unit length. So if you actually calculate the length of this, you'll get 1. That's correct. What you said is correct. So if you do this calculation, if you square this vector, you'll get 1. Okay. But this part, when you integrate, will disappear. Okay. Because when you integrate cosine theta from 0 to 2 pi, you get 0. You integrate sine of theta from 0 to 2 pi, you get 0. We're using symmetry arguments to say that only one part of the unit vector will survive the integration. And so what you're going to end up with is a k hat direction, something in the k hat direction when you integrate, which is a unit vector. Okay. All right, so I have this, and I have this. So all I got to do is put it all together. So let's put it all together. Okay, and then my dq is this. And then this is my r squared. Okay, this is going to be kind of weird because when I integrate, I have z's and thetas. But theta's constant, actually. That's not thetas. I messed up, it's alpha. Alpha is a constant. Okay. What did I get? Cosine alpha isn't the component along the z direction adjacent over hypotenuse. Is that an I hat with the R hat? Okay, where are you talking? Okay, so the I hat here, K hat here, and J hat here. Okay, as you're asking the question. This is R hat. Okay. This is the Z component. Okay. Now, I can rewrite cosine of alpha because it's a constant. It's a constant. I can write it in terms of these two because cosine of alpha is adjacent over hypotenuse. So it's going to be basically z over r. Okay. Yeah, and the question is don't we just want the vertical component? Yes, that's what we have, right? The z component is the vertical component. Okay. All right. Only the vertical component, the one out of the plane, contributes to the integral, and that's what this is. And like I said before, this whole thing is a unit vector. But when you integrate, only this one survives integration. This becomes 0. Correct. Well, it's hard to draw a unit circle. We're not working in 2 dimensions anymore, right? The unit circle. You would think of it as a unit sphere. Okay. You can't say unit circle anymore. You got to say unit sphere. Okay. All right. So that's it. And it looks complicated, but look at how hard that integral is going to be. I'm only going to integrate d theta. So basically, this is my integral. Let's do this. I would take all the constants out. Okay, so that's it. That's what I'm trying to integrate. And let me make that PowerPoint. Of course, when you integrate d theta from 0 to pi, you get 2 pi, which will cancel with this 2 pi. And so my total field then is the following. And I forgot a z. Because we take q z over z squared plus a squared with 3 halves in the half direction. Yeah, it's a nice integral. And you'll find that most of the problems that you'll deal with, it's the setting up that's hard to do, not the integration. The integrations are going to be pretty straightforward. Like on a test, if I actually gave you a problem where the integration is horrible, I would probably give you a list of integrals. Although since we're doing the test online, I'll probably let you use the textbook and look up the integrals in the textbook. Yeah, so remember, I'm not saying r hat is z over the length of the vector. The z component of r hat is z over the length of the vector. Okay, so. Great, r hat isn't that z over the length of the vector? right? This is z over the length of the vector. Okay? Okay. That's a z component. That's it. Okay. I didn't say anything about what the entire R vector is. I mean, I wrote it in terms of trig terms, but I didn't say anything over here. I just said that the z component of R hat is just z over the length of the vector. Yeah, just z, whatever this length is. What? This distance, which is z, and maybe because of the fact that I wrote down, I called it z, maybe I should have called it something else that might be confusing. Okay, all right, that's fine. You can come off it. You can ask me that question off the slides. Oh, okay. So a couple of questions. What does that ring look like if this number is big? Maybe I should have called it something else. Looks like a point charge. And what's the field of a point charge? So if you're really far away along the z-axis, this is going to look like a point charge, and the electric field should look like that. Oh, look at this expression. I'm hoping that if I did this right, I should get the same thing when z is much, much greater than a. And look what happens when z is much, much greater than a. If z is much, much greater than a, I can ignore this term. And I get k, q, z over z squared to the 3/2. This is z cubed. That agrees with our intuition. It looks like a point charge, then my expression should look like that for a field into a point charge if I'm really far away. Now, in the homework, you have a problem. Of course, in the homework, this will be along the x-axis. Okay. In the homework, you have a cylindrical shell along the x-axis. And they want you to find the field at this point P. It's not a good picture, but problem kind of looks like that. This part looks bad in the picture. But, in fact, I think my coordinate system looks like this. Okay, it should look more like that. So in the homework problem, I forget which number it is. They want you to find the field here due to this cylindrical shell, so it's empty on the inside. And they ask you to use this equation as the basis for solving the problem. It's number 13, okay. And I say, well, why do I want to use that? First of all, some of you might be thinking, wait, that's a two-dimensional object. Do I have to do a 2D integral? The answer is no. If I can break this up in the right manner, I can easily do this problem. What they want you to do in this problem is break this up into pieces small enough so that the field had the same value all the way on the dq. You know that the problem we just did The electric field at this point, anywhere around this ring, is the same value. So what we're going to do is break this up into a bunch of rings. Okay. In the problem, these are going to be x's. Okay. In the problem 13, this thing lies along the x-axis. So these will be dx's. And your dq is going to be lambda dx. So you're going to have, basically you're going to be using this expression, but you know the field due to a ring. You're going to change your q to a dq because you're finding the field due to a ring of charge dq. And these will be x's. And you're just going to integrate along the x direction. I thought it was hollow. Yeah, if it's solid, then you got to integrate a third time. I thought someone. Let me take a look at the problem. I have it with me. Yes, it's thin walled. It's a thin wall cylindrical shell. That means it's there's nothing on the inside. It's hollow. Now part B, that's true. Part B, it's solid. Okay. But you're right. Part B is solid. And so yeah, you have to integrate a third time for the inside. Okay. So this allows you to find the field due to a disk. Because if I have a disk instead of a ring, I want to find the field due to a disk. And this is solid. I'm going to break the disk up into rings. Okay, we'll break the disk up into rings. And the dA for the ring is 2 pi r dr, and the dq whatever the radius is. So for part B, then, once you've done part A, all you got to do is integrate along the ring, along the radius. Yeah, I think if it was a sphere, I would think of it as an onion because it's 3D. I would think of it as the tree rings in the tree, but however you want to think about it. And again, the intervals are all going to be easy, but it's really learning how to set this up. This is a really good problem because if you know how to do this problem, you should be able to do anything with cylindrical symmetry. What is after the dq? This is q over pi r. Here you go. This is an arbitrary radius. This is the radius of the disk. And so you would integrate over all the r, all over the, I'm sorry. You would integrate over all the rings that make up the disk. And then you would have the field loop for this whole thing. It's really a nice problem because you actually, your starting point is this. You're doing separate integrals each time. You're doing an integral for part B and an integral for part A and an integral for part B. But in reality, you can actually set this up as a triple integral and just do it right away. Those of you who take Calc 3, you can see how this is a triple integral. Okay. This is really what it is. It's just that they're making you do them separately so they look like single integrals. But it's really, if you use the methods of Calc 3, you set up one triple integral and you're done. Now, suppose that lambda was not constant, or let's say the charge density is not constant. The only difference is that whatever function you have, well, you won't be able to put a lot of the integral. So in the PowerPoint slide, you can see the integral d theta. If lambda in the problem depended, let's say, on, I gotta give you a good function that where the integral is not 0. Let's say if lambda depended on cosine squared theta, then next to the d theta in that PowerPoint slide, you would see a cosine squared theta d theta. And there is a homework problem where you do a ring where the charge distribution is not uniform. Pay attention to problem number 9 in the homework because you get practice on those. And then take a look at problem, take a look here, 14. In 14, you do a ring where the charge distribution is not uniform. It's actually half a ring. Now, the other problem I have is this one. And you do have a homework problem related to it, although P is at a different location. And if you look at the textbook, there's problems similar to this one in the textbook. And you know, the only way to get good at these kind of problems is just to practice them. It's really the same. If you look at it, it's just the same process every time. The hard part is writing dq, r hat, and r squared. That's the hard part of these problems. Because you're doing the same, you're following the same procedure every single time. And if you look at the big picture, whatever geometry I can give you, you're following the same process every time. It's just that the geometry might make it hard for you to figure out what dq, r hat, or r squared is. Really, that's it. Okay, so they should all, when you look at these, you should think of it, it's this type of problem. This is the process. I gave you the process, right? That part comes slow. And then movie software, video software is making the computer run slow. So you have this essentially method of doing the problem. Hold on a second. I'm having computer problems. Sorry, folks. My computer just acting weird right now. Okay, I'm just going to go to this slide so I don't have any more problems. Okay. Yeah, part of it. I mean, is this blurry? What you see right now, blurry on the board? What you see on the board kind of blurry. It's pretty blurry. Okay. On mine, yeah, it's a little blurry, which is troublesome. Hold on a second. Let me see if I can make any adjustments. I don't want my video. I don't want anything to be blurry. Does it make any difference? It seems like it. Okay, what's it saying? Yeah, I do have a tablet. I like walking around. That's my only concern. Sometimes it is blurry, sometimes it ain't. I apologize. Well, I'll try to write as large as possible. The board on the right, I'm sorry, the board on the left is clear, right? The board on the left clear? Okay. I'll write bigger, and I'll see what kind of adjustments I can make. And if not, I might have to resort to the tablet, which I don't like, but yeah, I'll try to write. I'll try to, as much as I can to write bigger. I apologize for that. Okay. Like I said, the other example, I will create a video for it. Yeah, maybe I'll have to get a better camera than this. Let's see. Let me try one more thing. Yeah, well, I need to change anything right now. I'll see if I can change the resolution and make it better. Okay, next topic I want to look at is the motion of charged particles in electric fields. Okay, I want to look at the motion of charged particles in electric fields. Basically, I want to look at kinematics. If you have a charged particle in an electric field that's uniform, the kinematics is no different than having a charged particle. I'm sorry, I'm not a charged particle, but a particle in the gravitational field. You've all done kinematics problems. You've all done projectile problems. The field is uniform. When you do a charged particle in a uniform electric field, it's really the same thing. But for some reason, when students do problems involving charged particles in electric fields, they have difficulties with them. I don't know why, but it's the same problem. Oops. Sorry. So if you put a charged particle in the field, and you want to look at the forces on it, you want to apply Newton's second law. You said that the mass times acceleration, which is Newton's second law, equals q times e. And so solving for A, we get that. If E is uniform, A is constant. And then you have motion at constant acceleration, which is a kinematics problem. And then if you want to look at the work done by the field, if the field is constant, that's what uniform means. Uniform means it has the same value everywhere in space. Okay. Okay. We're talking about static fields, so there's no time dependence, because in physics we say time independent and uniform. Those are two different things. Time independent means the field doesn't depend on time. Uniform means it has the same value everywhere in space. Okay? Uniform means the field has the same value everywhere in space. Time independent means there's no dependence on time. They're two different things. Okay, so if E is uniform, A is constant. And if you want to find the work done, and the field is uniform, then this is the work done. If uniform field. And according to the work kinetic energy theorem, this is the change in kinetic energy. According to the work kinetic energy theorem, then the work done equals the change in kinetic energy. So really this is basically the first, 6 chapters in Physics 205. Okay. You okay with that? Okay. Now, when we're dealing with particles that are small, we're going to be dealing with electrons and protons. I want to say a few things about electrons and protons and some of the units. First of all, when we're dealing with electrons and protons, you should write down the mass of the electron. Mass of the proton. And also, when you're dealing with kinetic energies, they're going to be small. Kinetic energies will be quite small. And we're talking about 10 to the minus 19 joules a lot of times. And so what we do is we define a unit of energy when we're dealing with small particles called the electron volt. 1 electron volt is 1.602 times 10 to the minus 19 joules. Okay. 1 electron volt is 1.602 times 10 to the minus 19 joules. And we're going to be using this when we're dealing with small particles. I might say, find the energy in electron volt. Like it might feel like in quantum physics we use electron volts a lot. Now another unit would be 1 mega electron volt. When we do a relativity and we're dealing with relativistic particles, you're going to be dealing with particles that have energies of mega electron volts. If you have a small particle, like an electron, and it has 1 joule of energy, 1 joule sounds like a small amount of energy, that electron is moving really close to the speed of light. If you look at an accelerator, like a Fermilab or in Switzerland, they're not even close to 1 joule of energy for the particle. Okay, they're about 1 million times lower than that. Okay. So let's do an example, just so we get to see how these, how we deal with the kinematics here. Okay. Like I said, this is really, if you have a particle in a field that's uniform, these are really not very difficult problems. But for some reason, when you apply these ideas electric fields, students get stuck. The same thing as the projectile problems. Okay. All right. We have a particle of mass 1.2 times 10 to the minus 8 kilograms. And the charge is -1 millicoulomb. And you're given the velocity, an initial velocity, of 3I minus 5J times 10 to the third meters per second. And it goes in a region of a uniform field where E is given by the following. Minus 6I hat plus 2J hat. Times 10 to the fourth meters per coulomb. I want to know the acceleration of the particle. So remember that we had F equals Q times E equals MA. A is Q E over M. And so really this is just plug and chug kind of a problem. 1.0 millicoulombs. And this is the electric field. Over the mass of particle. And so now you put the numbers in the calculator, and what you get, finite values. The following. This is new. Sorry. Now, it says 5.0 I hat minus 1.7 j hat times 10 to the plus 7. Okay? Does that seem like a large acceleration? Actually, it is. But when you're dealing with small particles, you will typically get accelerations this large. And so they can quickly, particles, if you accelerate them over a sufficiently long distance, they will get close to the speed of light. Okay, so this is typical for small particles because they're so light. Now, what's the velocity after 3 microseconds? Well, we know that A is dv over dt. dv is a dt. So then v is the integral of a dt. So all I have to do is integrate this with respect to time, and I'll get my velocity. Of course, I have my constant integration too. Okay. I have my constant integration. So v then is going to be the integral of this expression and what is that going to give me? What's a constant? And guess what my constant is? My constant is my initial velocity. So this constant of integration is just going to be this value. I'm going to take this guy, put it in here. For t, I will substitute the 3 microseconds. And so my v pardon my back. That's it. And if you simplify this, you get the following. Okay? Okay, so if you can't read this, so it's probably because I'm having internet connectivity problems, but the video that I'm recording, you can see this clearly. So the final answer is 3.15 I hat minus 5.05 j hat times 10 to the third meters per second. So if it's really blurry right now, it's probably because of my connectivity. Okay, because the screen I have, when I look at my screen from my video, it looks better. Probably than what you're seeing. It's pretty clear. So I apologize if I'm having internet issues. Okay, so probably all the issues you're having is probably because of the connection. And one of the reasons is there's two of us who are working and using the same line. Both of us are using either Zoom or WebEx. Okay. All right. I want to know the displacement after 3.0 microseconds. I want to know delta R, so I don't have to know the initial position. I'm sorry. Yes, this is 3 times 10 minus 6. Sorry. It's 3 microseconds. Okay. So again, how we get this? Well, we know that V is dr dt. dr is v dt. The delta R is the integral of v dt. And since I want delta R and then R itself, I really don't have to worry about the constant integration. So all I got to do is integrate this with respect to time. Actually, not this one. I need to integrate this with respect to time. Okay, I integrate this with respect to time. Right here. And then put in 3 microseconds. Okay, so let's integrate this with respect to time. And this is going to be pretty easy, right? When you integrate this. C was our initial velocity, so let me write that down. Then you substitute the 3 microseconds in. And I'm suppressing the unit, I'm getting rid of the extra digits here because I don't have enough space. Okay. And so when I simplify that, I will get 9.22 I hat minus 15.1 J hat, the whole thing times 10 to the minus 3 meters. Okay, that's what you get. Just 1 second. Are we okay with that? I will ask you one question you should try to solve at home. It's the following. Suppose I have 2 plates. Okay. Now these 2 plates, one's positively charged. The other one's negatively charged. When you have 2 plates like that, especially if the plates are large compared to their separation, what you'll end up doing is you'll be creating a uniform electric field that points downward in this particular case. So let's say E is constant. Okay. So let's pretend that we have a positively charged particle with initial velocity v in the x direction. This distance is L. As the positively charged particle goes through that field, what's going to happen to it? It's going to deflect downward. Like the particles do this. It'll get deflected by a distance delta y. With respect to the center line. So the question is, I'm going to leave this up to you. So this is V initial I hat. This is plus Q. We go right into it. The particle is moving that way. When it comes out, it's going to be somewhere over here. And the question is, can you derive an expression for the deflection? This is a lab that when the class is on Brown, this is a lab we do. We actually measure this in the experiment. Okay, but we can't do that this semester. This is a problem that you should learn how to do. This is a pretty straightforward problem, just kinematics. It's no different. This problem is no different at all compared to if I take an object and I roll it off or slide it off the table. And measure how far it has fallen after, I don't know, a couple seconds. It's the same problem. You have a charged particle coming in with initial velocity v sub I along the middle in between these two plates. And you want to know how far it gets deflected after this thing travels L in the field. It's no difference than an object sliding off a table and you're calculating how far it travels downward after a certain period of time or after it's traveled a horizontal distance L. No different. It's a projectile problem. Really, this is a problem you should know how to solve. Okay. We have a homework problem where you go through the kinematics of these a particle in a uniform field, and I have you answer all kinds of questions regarding it because it helps you to review your Physics 205. Okay, I'm going to actually stop here because I want to send the email to you guys regarding the, I want to make sure that you all got the email regarding the lab kits, okay? I also have a class at 11, but we'll get started. Any questions before I end the meeting? Is the picture clear right now? Barely, okay. It's got to be then it's got to be then my connection. But I apologize for that. I can't, unless I go on campus and teach the class on campus. When I post this video on Zoom, let me know how it looks to you guys, okay? Because it's hard for me to see what it looks like, what you're seeing. I can't even see what you're seeing. Okay, so I'll stop here and I'll send the email. Sorry about all the issues with the video. I apologize. Take a look at the YouTube video when I put it up. All right, I'll talk to you guys later.